All right, well, welcome everyone. So both in person and online. We'll start by looking at the 1-minute papers from last week. So one of them was just saying type system. I'm not sure what this means, but this whole course will be about exploring the type system, so it's fine to still be a bit overwhelmed by it. We'll hopefully make it easier for you to navigate it today with our lecture about exploring the design space and finding the different sort of types you can give to the program you have in mind so that it's well behaved. Then there was a question about the difference between functions and proofs, and they're essentially the same thing. So this will be either tomorrow or next week. We'll see a bit more about like this whole design philosophy, the correspondence between statements and types and proofs and function implementations, basically.
Yes and no. There's a kind of qualitative difference. Like, it's not really exciting to say if it's a natural number and if there's another natural number, then there's a natural number. But that's the type of adding up.
Right.
It's not a proof of anything terribly exciting, but you can nonetheless see it as a proof. But you care about slightly more than that. Right? When you add two numbers, you care about which number comes back. So sometimes when we're programming as opposed to proving, we give more of the monkeys about what the inputs are and exactly what the output is. And we might prove stuff about the program to show that you did it right. So they work the same way, but they don't always feel the same way.
Yeah, but the same constructs can also be used both as like proof constructs or programming constructs. So it really just depends on your point of view about what you feel like this function is for. Are you going to run it? Are you just building it to prove to yourself that the thing was well designed? Like this is where the separation is.
Yeah.
But morally, I mean, from the point of view of the system, they're exactly the same thing. Yeah. It's more of a judgment that you make on the programs rather than...
We've been doing this for long enough that language will slide between the language of proving things and the language of programming. You know, we'll talk about a function type or we'll talk about an implication because we can't remember which one we're doing anymore.
So to spin it positively, if you can program, then you can prove.
Absolutely.
And then there was a question about subst, and this is really important. It's normal to still be a bit confused because equality is like one of the hardest thing, if not the hardest thing, to understand in this course. So I thought we would go through maybe a reconstruction of subst and the notion of equality through some steps. So if you've already started the coursework, you've seen that we have the type of Booleans, which is, so it's an inductive type. So its own type is set, and then it has two constructors, true and false, each of them having exactly the type bool. And then one thing we could try to say is, okay, well, I got a Boolean, but I happen to know that it's the Boolean true. And then you want to express this somehow. So what you can do is you can introduce an is true predicate. So it will talk about a Boolean. So its type will now take a Boolean as an argument, the one it's talking about, and then it will return a type. So this is how we define like an indexed family. And it has a single constructor. Let's do it like this. And this constructor is just constraining the index to be exactly true. And so when you're saying that is true, you know that is true B, you will know that this only way to construct this proof is to use the is true constructor, and therefore B must have been known to be exactly true at some point. So the corresponding substitution principle for it goes something like this. If I have an arbitrary predicate over Booleans, and I know, okay, I'm going to throw in a variable, and I know that P of true holds Then if I know that B is true,
Yeah, you need to rename something.
mm, right, I have a predicate of the Booleans. I know that P holds of the true Boolean, and I know that little b happens to be true. Therefore, I can prove that P holds of B. And this is implemented by, okay, so here we have the proof, and here we have P true, and here we have the proof. So if we look at the goal, we have this constraint here saying that B is true, and then we have the proof. And by pattern matching on the constraints, we have the magic of dependent pattern matching. So Agda figured out that for this is true constructor to be a valid pattern for the is true of B type, it needed to make the B equals true constraint hold definitionally. And it could do this by saying, okay, well, I will now consider B to be true. And so if you look at the type of the goal now, B has been changed to true. And so you can now just use the assumption you had in the context. And you can do the same for is false. So let me just do a bit of copy pasting and then search and replace of true with false. And this works again, because for the same reason, now we have the opposite assumption that B happens to be false, and we can do this substitutions.
There's something important to say about the machinery that's at work here. We've got types that represent certain kinds of knowledge and data that stand for evidence that something happens to be the case. It might seem a bit mysterious about how and when Agda deploys this information. It doesn't casually do magic. It doesn't kind of bridge logical gaps whenever it feels like. The crucial move was the pattern match move. It was saying, I want to look at which constructor made this data that forced Agda to solve some equations and figure out that if this data is going to be made with the isTrue constructor, that B had to be true. So that was the provocation to do the reasoning. It doesn't just do reasoning any old time. It does exactly the reasoning you tell it to. And telling it to pattern match is one way to provoke enough reasoning to do a constructive case.
So another way, which I've highlighted by editing the code here, is to explicitly pattern match on the Boolean. And if it's true, then you don't actually even need to inspect the proof anymore. But if it's false, then you have a contradiction, because if you try to actually pattern match on the proof, you will try to unify true against false, so declare that the two of them are equal. And this is just impossible because all constructors are always seen as intrinsically distinct from each other. And so you can use this absurd pattern to just say, this case just doesn't make any sense. And then Agda will actually check that, yeah, indeed, if I were to try to pattern match on this, it would just fail.
Is this the first time we've had the observed pattern? Sorry, I missed last
I
week.
don't know.
I think so,
Yeah.
Yeah.
I also missed
you
last
could
week.
maybe change it to an X and then
Oh, yeah.
K-split on it. But,
Yeah.
So if we look at it, yeah.
If you're old enough to remember One Foot in the Grave, but the absurd pattern, well, which we're about to see, it's basically Richard Wilson saying, I don't believe it. It's a kind of, except it has the magic power to get him out of the situation. It's saying, this can't be happening to me. I don't have to give you a return value because I couldn't possibly be in this situation.
yeah, so we didn't have to give a right-hand side because that pattern was impossible, right?
Yeah, so this is essentially telling Agda that this is a dead branch and we'll never actually enter it, and so it's fine to not even give a right-hand side, as you said, because it will never reduce.
But ACT is not clever enough all the time to spot when that's the situation. So this is the mechanism for putting your finger on it.
Yeah,
To say, this is the impossible thing, so go away.
yeah. So the absurd pattern is a pattern like any other. Here it happens to be at the top level, but if your impossible thing is deeply nested, you can split recursively a lot and then eventually expose an absurd pattern to say that you are in an impossible case. All right. So we had is true, is false, but it's a bit annoying to be defining exactly the same family for intrinsically the same concept, and then the same substitution functions. I mean, you saw it, I just did search and replace. So what we can do is that we can define is, which takes a Boolean as a parameter, a Boolean b, and then is also indexed by a parameter, by a Boolean. So the distinction here is that b will be constant across all of the constructors, a bit like a in list of a. So this is why it's to the left of the column. And then on the right-hand side, we have the index, which may vary in the constructors. And this one will be potentially refined in each one of the constructors. And this returns a family. So we could say, okay, well, I can have is true, true. Or I can have is false, false. And then I could prove subst is, which is going to be fairly similar to this. So let's see if I have P of C, and I know that if I have P of B, and I know that B is the same as C, then I can have P of C. Okay, all right, that's true prime.
No, the problem is that you're not allowed to change B to true.
Yes, the problem
Oh,
is that you're being more Catholic than you've asked.
all right. Right, so this could be an approach, but again, we have essentially the same pattern in the two constructors. We have true, true, and false, false. So instead of saying, like this case, instead of spelling out all of the possible diagonal cases, we can just have a generic one by, as I said earlier a bit too quickly, putting the b as a parameter and then saying that b is the same as b. So if you specialize that, you can redefine is true, the predicate now, just in terms of is, by partially applying it. So you've gone up in generality, now you're handling both, you're defining both of them at the same time, and it also means that you can define the eliminator in just one go. So this will go just like the previous thing. So here you have P of B, and here you have the proof. And by pattern matching on the proof that B is the same as C, you will have the new goal which says, okay, well, Agda here decided to pick B over C, but it could take C over B, like we don't care. They're both the same. So now the goal is PB, and we have PB in the context, so we can define it this way.
Yeah.
And then,
So once again, it's the act of pattern matching that provokes just enough reasoning to solve the equations, which turns the C in the goal into a B, and there's your actual miracle of transubstantiation. And that's why some people refer to these things that live after the colon, but you're allowed to make specific, so right? So
broader
here,
down, yeah.
Wherever it got to here, this thing, because it's abstracted, so this thing scopes over all the constructors, and you have to put B here as the first parameter. But the things to the right of the colon, you're allowed to choose those to be very specific things. And here, we're choosing the second input to be the same man as the first input. So that's going to get you some equation solving. But before we did the pattern match, C was merely known, we merely knew something about C that related it to B. After the pattern match, C is B.
And if you have really complex constraints between the different arguments in a type family, it might be that Agda refuses to k-split because it will say, well, I'll see no obvious ways of making this hold for sure. So then you will need to be a bit more explicit about why it holds. Maybe by doing some more pattern matching so that things compute a bit, maybe by doing all sorts of things. But when you have very simple cases like this, where you just have variables and constructors, it should always be able to do the split, observe the constraints you are demanding hold, and then just make sure they hold by changing the types of the goals, etc. Because you've exposed the case.
Colors is clear. Yeah, it's exactly. Variables and constructors give rise to easy equation solving problems, because if you've got different constructors, they just ain't equal. If you've got the same constructors, they're equal component-wise. So the problem simplifies. So if your problem is made of red constructors and purple variables,
You're golden. Yeah.
if you've got anything else showing up in the problem, it's
It's a lot tricky. Yeah.
So watch out.
So of course the last step is to actually go to equality. So instead of having a family for each possible type, so is at bool, is at nut, is at function types, etc., you can just define equality, which is parameterized so implicitly here, so that we don't need to explicitly say which type we're talking about. Type A, and then a term at that type A, and then you once again have a family, so an index. And this is exactly the same constructor as above. You're saying, well, A equals A. So this is how we arrive at equality, is this generic definition of equality and the associated substitution principle, which is, once again, if you have, I need more variables. So I'm saying A is a type, and X and Y will have type A. So if I have a predicate over A, and I know that X is equal to Y, then any proof P of X will do for a proof of P of Y. And this is, I'll do the eager pattern matching already. And you can see, oh, I guess I was taking the proof in the other position in the other cases, but this is essentially the same thing. Modulo permutation of the arguments. So hopefully it's a bit clearer how substitution works and what it means to equalize like the left-hand side with the right-hand sides when we pattern match. All right.
Okay, should we move on to today?
Yep.
So I'm going to start. We're going to do just some programming to start with, like we could have done in Haskell, and then we're going to see how far we can get. So I wanted to find a lookup function on lists. So I better define lists first, and I better define natural numbers so that I can look up the nth element in a list. But let's start with lists.
Oh.
Sorry. How do I get that?
Forgot.
The non-French keyboard.
Where is it?
You'll never get me on that thing.
Oh, here.
All right. Okay, so list is not a data type, and we're going to have lists with elements from some set A. And it's going to be a set. And I think in the coursework you have forwards list and backwards list, but here we're just going to do the forwards list, so I'm not going to put any kind of directional thing in the name here. And I'm probably going to screw up the names compared to the coursework, but I'm going to say a list is either the empty list, which is a perfectly fine list, or a list consists of an element from A and a tail list, and that's how you get one more list. Right? So I have one constructor, it has 2 places for arguments, and it's a forwards list, so I have the A first in the list here. And the way to remember it is that this thing is pointing to the big thing, the list, rather than the small thing, which is the element. Right? So I can make the empty list, and then I can make a list where I put an A in front of the empty list, and I can put a thing in front of that, and so on, and that's how I make my lists. Right? And we've seen the natural numbers already. So it's something similar to the lists, but I don't have a choice what element to add on to things. There's only one thing, right? So there's either 0, which is a lot like the empty list, or there's suck, which says that if I have a natural number, then I get another natural number. Right?
Yeah.
So
Very helpful to realise that a natural number is a boring list. The things are likely different. They're just spuds.
yeah. So if you define the unit type, which has exactly one element, then list over the unit type, if you choose A to be the unit type, is exactly the natural numbers, right? Okay. I don't know what you mean by the variables here. Do you want me to declare some variables?
Yeah, for
Okay.
natural numbers, maybe.
Right, so n is a natural number, xs is a list of A, I suppose.
Mm-hmm.
So Guillaume already defined that A is a set in general. So that's why I can say, okay, a list of A, xs.
It's singular.
Okay, so let's try to define the lookup function. So we take a list and we want to look up the nth element in the list, and that's what we should return, right? So lookup of x's and n equals something. Okay, so how should we do this? So now I have a few different choices, right? I could pattern match on the list, or I could pattern match on the natural number. And I probably want to do both, so I'll start by pattern matching on the list. Okay, and in this case, I can pattern match on the natural number. So if I want the 0th element of this list, well, that's good news, because I have it right here, right? This is the first element of the list, and that's the one I want, so I can return it. Okay. Whereas if I want the nth plus 1 element of this list, well, then I don't want this one, but if I take the nth element in the tail of the list, that's overall going to give me the n plus 1th element in the whole list, right? So I can do a recursive call here. Look up x's n. Right. Okay, and Agda's happy with that because the list has gotten smaller and the natural number has gotten smaller, so things are getting smaller and we are going to terminate, right? But what about this case? So here I want the nth element of the empty list. So I could pattern match on the n, but it's not really helping me because if I want the first element of the empty list, then I'm really hard pressed to deliver on this, right? Because I just don't have any element here.
A is some arbitrary type about which we know nothing.
Yeah,
The only thing we could possibly know about A is what's locally in the context. And if you
Look at the
context, you'll see the cupboard is bare.
yeah. So for all I know,
A set about which we have no clue.
for all I know, A could be the empty type with no elements whatsoever, right? In which case it's rather hard to give back an element of A. So here it was fine because we had a list and we just got the data from the thing that were given to us. But in this case, we really have nothing to give back. So that's why this section is titled oops, right? So in Haskell, we would just leave this out and then we would run our program and then our boss would come and we would demo it and it would crash at the most inopportune time, right? But in Agda, we don't like crashing at the most inopportune time. So I'm going
That's the thing. In Haskell, you tell lies.
Yeah.
Because it's inconvenient not to. Right? You say this thing exists, and then when the moment comes, it just falls over.
Yeah. Sorry. Go on.
Okay. So the question is, can we say something more precise that's actually true?
Yeah. So one easy way to fix this, which is what we will probably do in Haskell, is that we would say, okay, it was too much to say I can always give back an A, right? That's just not true. But I can give back maybe an A. So I can change this function into one where we are honest about not always being able to return an A, saying that, well, sometimes we're just going to return nothing, and sometimes we're just going to return an A. So let's define maybe. So this is exactly as you know it from Haskell. So we take a parameter A and we say, well, there's a just constructor, which says if you have an A, then you have a maybe A. And there's a nothing constructor, which says that, well, you can always have a maybe A. Okay. So we take the old function, but rather than returning A, we return maybe A. And now things are a bit easier. So I can pattern match on the list again. And if it's empty, then I can just say nothing, right? If it's non-empty, then I look at the end to see which one do I want. If I want the first one, then I return just of x. And if I want the n plus one, then I can again do a recursive call, look up x's n. And that will give me a maybe A, but that's okay because that's what I want, right? So, and again, things are going down, so this is terminating, and that's fine. So that way we don't have to tell a lie, but on the other hand, if I don't show you the implementation here, I just show you, okay, look, I wrote this function, it has this type, then you have no idea if I've been lazy and just constantly returned nothing, right? I mean, maybe I couldn't be bothered to actually define this, and I want to go home, so I just...
Yeah. So it could be disappointing that way.
Yeah.
And also, just from the point of view of the rest of your program, you're just living in constant fear that a lookup didn't work.
Yeah, so if I put this in my library and you use it, then you have to constantly just checking, did I return nothing or not, right? So maybe there's a better way to do this. So we thought we'd just drop you straight into this one.
Can I use Guillaume's keyboard?
Well, it's a non-event mode.
Let's see what happens. All right. So the key thing that's missing is some idea that the number, the position that we're looking up, is small enough to point to something that's actually in the list. Which means it might be useful to have a bit more of a handle of how long the list is, right? So we're going to just get a bit more leverage out of types by saying, oof, maybe the type system should track the length of the list. And we do that. I see the types are handy here. We're going to define what it is to be a vector storing elements from some given type, A in set, and it's going to be indexed over natural numbers, and the natural number is going to tell us the length of the vector. Do I need,
Or define a...
What do I do? Is it backslash?
You could define an alias, right?
Backslash bn. Shocking. Thank you for doing variables. So I can say, well, there's going to be a nil and a const. We make them the same way we make lists, and we even overload the constructors.
So 0 is spelled 0, okay, like that. So the nil constructor is constrained only to make vectors of length 0. And then the cons constructor takes an A and a vect of some length and gives back a vect, same element type, but length 1 longer. Will it cope with the implicits? Let's see what happens. Yep. Right, everything's good. Notice that these indices that are in the Catholic position that are specific to the thing that's abstracted after the colon are all very nicely red and purple, which means when we say solve equations that are specific to this index, it's going to work. Okay. And next, so we've figured out how to make lists that are a specific length. Now we need to figure out how to make numbers which are small enough. So the idea here is that natural numbers, they have a 0 and a successor. They're an infinite set. We want to talk about a finite prefix of the natural numbers that has exactly a known number of things in it. Right? If our vector is of length n, then we want to index into it by a number that's less than n. And there are various ways we could cook that up, but I'm guessing the way Guillaume wants me to cook it up is to say, let's have data thin, and again, we'll abstract an index nat to the right of the colon. And what do you want me to use as the constructor names? Just 0 and suck?
Yeah.
Again, we're overloading the constructors. So, okay, we want to say, when are we allowed a 0? Right? How big does the set have to be to... Oh, yes, thank you. Thank you. Quite right, too. So how big does the set have to be to have a 0 in it? Well, no, if this, we're talking about the index, the number it has to be at least 1. Okay, so this is fin suck n. You know, if the set is any positive size, it's got a 0. And then here's the trick. It's a bit of an aha moment. If you've got a number in fin n, that's to say a number less than n, what can you say about taking its successor? Its successor fits in the next size up. So it's kind of a bit weird that you build, that you take the successor of a number from one finite set and it ends up in a slightly bigger finite set. It's actually just worth, is it worth? Just looking at, foo in fin, suck, 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 0. Foo equals. Right, I don't know if you've shown this yet, but Agda has this wonderful facility which uses the type as a clue to kind of search for anything that could possibly fit. So it's a bit like Googling. So I type Control C, Control A is find what's the first thing you think? It's like putting the type into Google and hitting I feel lucky. You'd be surprised how hard it is to make sure your homework isn't susceptible to Control C, Control A. It's not cheating. When the type says there's only one answer, you're entitled to that answer. Right, if I say minus L and do Control C, Control A, that's like give me the top however many hits. You could give me the top 10 hits. And it's saying because we've got an upper bound of 3, we can make the 0 where n is 2, or we can take a successor of the 0, and this 0 is the 0 with n is 1. This was the 0 in fin 2 that ended up successored into fin 3. And then this is the 0 in fin 0 that got successored into fin 1. So this is the 0 in fin 1 with this n being 0. So this is the 0 from fin 1, successored into fin 2, successored into fin 3. Okay, so now I think I'll just, well, I'll leave that there.
Yeah.
I'll leave that. And then if we do lookup, now,
Maybe pick your favorite number so you don't have an open goal.
okay. I'll just hit I feel lucky. Okay, so lookup takes some vect a n and a fin n. I'm not allowed to call it lookup, am I? I'll call it vlookup. Oh, no, stop. Right, so here we've got a fighting chance of keeping a good promise. We really want an A, not an A if you're lucky. But we know how long the list is, and we know this number is small enough. Got fighting chance. Yeah, I keep not hitting the control key. Yep, I need a question mark, don't I? I need a question mark. Right. So, let's see what happens. I'm going to look at the... Oh no, it's tap click. Why is my keyboard not responding? What have I done?
Text is read only.
You're in override mode.
How do I get out of that?
Can you set key somewhere?
Top right. Ooh.
We're back in business, thanks. Right. We look at the list, and I genuinely don't know what's going to happen. See, that's really clever. It's not really clever.
Mm-hmm.
It's looking, that's more magic than we asked for, which is slightly annoying. Right. It's actually figured out that only one case is possible, which is really, really smart. It didn't used to be this smart. 10 years ago, Agda was not this smart. It's figured out that cons is the only case possible, because if the vector was nil, then n would be 0, and then there'd be no way to make I, because you'll notice that these finite sets are inhabited only when they're size definitely not 0. So it's gone, just doing a little bit of look ahead, figured out that nil is completely impossible in this situation. And you'll see, if we look at the goal in the context, it's actually figured out that the I has to live in fin successor of something. Right? It's the only way it's figured out that the list has to be non-empty, and therefore that the number can't be in the empty set, fin 0. So now, when we look at I, it can be either 0 or a successor. So in the 0 case, we're really cool. We're happy that x, we can just get back. Now let's look in the successor case. You can see, well, we figured out that n had to be non-zero. So there's a head here and a tail. The tail is now some n long for some n. But the index is successor of something. And the something is small enough to pick something out from a vector of length n. So we can make a recursive call. Let's see what happens. If I say, I feel lucky, no. I feel lucky, ha, it just gives me the x. Okay, that's fair. It did know an element of the output type, so it chose the first thing it could think of. Let's say, can you think of anything else, please? Oh, it said, I can think of 2 solutions to this problem. There's the element we've just exposed by taking the list apart, and then there's what happens if we make a recursive call that happens to be well-timed. So you could think, which of those do I want? And what I say is minus S1, that's skip 1. I feel lucky. Right. And that's the point. It might feel a bit like cheating to ask the computer what type checks and just say, of the things that you can come up with that type check, I want that one. But think about it. You paid, or we paid for that outcome by bothering to tell a precise truth when we wrote the type down. It's like magic, but like not magic. It's like the way magicians actually do magic, which is there's a whole pile of a setup. There's sort of blether. Then there's some wiggling around with your hands and stuff, trying to fool the audience into thinking that that's when you're doing the trick. The trick was already done. And then you collect the applause. Right. So the point was, we pretty much did the trick when we realized what was a good type to give to lookup. And the rest of this business was just being pulled along by the right design choice to get, well, you know, in the end there was pretty much, there were only 2 functions we could vaguely sensibly write with that type, namely always give back the head of the list or give back the thing that's in the right position. You know, the type had pretty much, you have to work quite hard to come up with a different solution. I mean, you can, there are other solutions with this type, but of the things that are kind of reachable easily, that's, you know, the right answers are much closer. So this is a big overarching message, is that when you've got enough types to tell the truth, they actually attract you towards the good programs. It's not that programming with precise types makes programs harder to do. I mean, that would be the case if you were just in a situation where you wrote ASCII garbage in an editor and eventually asked the type checker to look at it. Then making the type more precise is making the target smaller and putting it further away. But that's not what we're doing. We're working with a computer to say, this is the solution space of the problems, and it's actually really well specified. And what are the things it makes sense to do in that situation? So making the programming interactive is what's key to making the precision survivable. Right? You can't be precise. It's difficult to take all of the burden of that precision on yourself if you're just dreaming of a program in the bath. But when you're actually getting help from the computer all the way along, then your precision rewards you by really cutting down the things that make sense to do and what's even worth trying. All right, how are we doing?
We have 5 minutes.
It's 10
Yes.
to.
Well, I can just throw in a bunch of concluding remarks. So as we saw, there were more than one program. Actually, I wanted to try something. Right, I need to switch back, of course. So let's see, because Agda had an inclination to pick the head every time. So what if I were to tell it to pick anything it wants, but it's also allowed to k-split. That's what -c is saying. And yeah, it's coming up with the head function. So this time it decided to print the impossible case. Yeah, different system, different outcomes. But so there's also this powerful option that you can pass to auto. But the point is that with this type, as we saw, there are more than one inhabitants. So that's what we were suggesting then with the next step. It's to actually have a data to definition, an inductive family, that describes what it means to have the ith value somewhere inside the list. So you'd have two constructors, one for like the 0th value on a non-empty list, and then one for something that's further down the tail. And then you could write a very precise lookup function that takes a vector, takes a k, and then returns not only the value, this is the sigma type, so a dependent pair of a value first, and then a proof that it actually is at that position in that list. So that if later on in the program, you need to remember where that value came from, you actually store that information and it's available to you to use. So that's one thing. Maybe you can try at home if you can come up with the constructors for this family and then actually implement the function. And then we saw a bunch of definitions and we guided you through the happy path, but there are way more paths you could have taken in that design space. So you could instead constrain the input in a different manner. So, okay, maybe here we just have an A, we don't need the most precise type ever. And just say, well, the index we're looking up in the list is strictly smaller than the length of the list. But the length, this time, it's going to be a function, not a straight-up constructor, so the splitting might not quite work the way it needs to. You might need to do more case analysis to reveal that the length actually computed down to 0 or to a successor so that you can do some further splits. So this might be a bit annoying. Or you could have written something like this, going back to our more precise type. We're saying, well, I have a list, I have an index, and either the k is too big to index somewhere in the list, or I actually have a very precise thing about like getting a value and a proof that it's at the right position. But what you're doing here is that you're sort of mixing up different things. You're mixing up checking that this is a good index and also actually returning a value for the lookup. So this is what I was doing, trying to explain with the Unix philosophy. It's like, we want to write programs that do one thing and do it well, looking up, checking it's a good index, and then that work together by composing them. So we're in a functional language. Composition of different functions is really cheap. So we might as well just decorrelate the checking and then doing the guaranteed valid lookup. And then finally, the one thing that's out of date now, we have our approach in the Unix philosophy is only handling text streams. So now we're able to express a lot of structure on the data we're taking in. So this is one thing I would not follow in one programming in Acta. But the other pieces of advice are pretty good when it comes to actually coming up with your own types for your functions.
Yeah, I quite like this last type actually, in the sense that it's kind of the working out of the maybe version. So it says, you know, you give me any old number, we're not fussy about that. But then if you want to make use of this result, then you've got to do one of two things. You either got to put up with the fact that there's a failure case and figure out how to handle that, or you have to do the proof to show that this case is impossible, in which case you're sure that you're in this case, which is the happy path. But it's kicking the can down the road, saying, it's the person who uses this function's problem that the type is imprecise.
So it's a good type if you suspect that I'm lazy and only return nothing, right? I'm not allowed to do that anymore because I have to show you that the index was too big. But it's not such a good type if you want to reuse this later, because then you have to redo the checking, right?
Yeah, in a sense, it's a very good error message, this first component, because it has a lot of structure that you can use later on, rather than just being a string saying the length was too small for the index. All right, yeah, I think that's it for today.
Are there any questions about any of this?
Do we have anything from
or online?
online?
No.
Yes.
Yeah, the room is really big. So.
The room is a bit echoey.
Yes. It's kind of funny how the room is. The room feels so much older than the building.
Feels like an art gallery.
Maybe we can stop the recording.
Yep.